Welcome, Woodstock students, to a discussion of motors and how motors depend upon voltage for their spin rate, and to look at the ideas of predicting spin rate under no load and real load conditions. Hopefully, in a few minutes, that will make a lot of sense to you. On the left, you see a small DC motor with a spindle that will rotate, say in this direction here, when it is connected up to a battery. And so I'm just showing a sort of cartoon version of hooking up the battery to the motor. And I think it's reasonably intuitive that the battery here will provide energy to the motor, and that electrical potential energy in the battery gets converted into a rotational energy out here. What also might be relatively intuitive is this, that if we could somehow change the battery voltage, if this was somehow a battery with a dial on it, or simply just replace the battery with a 1.5 volt battery, got replaced by a 3 volt battery or a 9 volt battery and so forth. As we increase the battery voltage, as we put more energy or make more energy available on the input side of the motor, the rotational motion of the motor increases, the spin rate of the motor increases. So that, I think appeals to our sense of conservation of energy. If I have more energy available here, there should be more energy available out this way. And if I need more energy out on the spindle to spin something faster, I'm going to need to put more energy in. So that part, I think, is pretty straightforward. I'm going to scooch down a little bit here on the slide and kind of just reveal one idea, which is this. We often talk about no load conditions, and no load means that the motor looks exactly like this, just the spindle itself, nothing attached to it. We're not trying to interact with the outside world in any way, just simply trying to get the motor spindle to turn, which is interesting but only so useful. So let's continue to examine that, and then we'll look at what it means from a practical sense as we try to make something else happen. Okay, so if we take a look at this so-called no load scenario here, we have this fairly straightforward linear relationship. The output velocity, the spinning rate of the spindle in revolutions per minute, RPM, depends on the input voltage that we attach to the motor. And it's a perfectly linear kind of relationship. With no voltage, of course, we get no spinning, and with the greater and greater voltage, we get greater and greater output velocity. Up to a certain point. There's some physical limitations here. If you tried to connect 1,000 volts to this battery, it's quite likely the battery would burn up and fail to operate within just a few moments. But other than that, it's a perfectly linear kind of relationship. Well, here's a picture of a motor that has a load, some kind of a rolling system, conveyor belt system, if you will, that picks up some mass and slides it up to the top of some ramp here. Just some kind of conveyor belt delivery system that's at some angle and so forth. So we're not showing the power input here, but just rather the spindle right here connected to this drum, and then a tight belt where both this drum and that drum are free to rotate. So this is a kind of cartoon picture. There's a lot of scaffolding here that we don't have in place, but you can imagine now that instead of just the spindle turning, we have to be able to turn this cylinder, and the cylinder itself is kind of loaded down, if you will, with a band of some sort of belt that wraps around both. So we're not just turning the spindle, but we're turning the spindle. It has some friction against this band, and the band itself is turning this other spindle, and now there's a weight on it and so forth. So you can see there's a lot more that we have to overcome if this spindle is going to turn. Okay, So that has an impact on the graph we were just looking at. Okay, so let me reveal that. Okay, here's the velocity again, shown under a variety of conditions. Okay, here's our input voltage of volts, and we've got our blue line here, which is the no load scenario. And then the red line is with some kind of a load, some kind of an outside object that's connected to the spindle. And then the purple one is kind of with a heavy load. And maybe we could think about that this way. Perhaps this red one is what we get when we just connect this cylinder and nothing else to the motor. It would reduce the output velocity by some percentage. But if it was just the spindle, it would reduce it by, I don't know, it looks like maybe about 50%. But then maybe when we connect up the band and the second cylinder and the weight, that's an even heavier load. That's a lot more resistance to turning, if you will, and that produces a much more dramatic drop in the output velocity of the motor. So motors will come with certain ratings, how fast they can spin and maximum input voltage and current that they need and so forth, but often those are expressed as no load situations, what it can do under no load. Okay, so I'm going to pause this here as a sort of first look at the relationship between batteries and motors and the ideas of load and no load, and we'll look at some other situations in another video.